Good morning to all the participants for today. Am I audible? Okay. Today we will start a very important chapter, kinematics of fluid flow. You see, the mechanics of any substance, any medium, any particle, whatever you call, basically relates between the forces acting on it causing the motion and the motion. For an example, we know the conservation of momentum, that is the Newton's second law of motion, relates the rate of change of momentum to the force, that mass into acceleration equals to the force. So, therefore, based on this conservation equation, the equations which are developed relating the force and the motions caused by the forces forms the background of the mechanics of the medium, the studies on mechanics. So, therefore, the first essential thing is the information on the motions, which is basically known as kinematics. Okay. So, now today we will discuss about the kinematics of fluid flow. Now, kinematics of fluid flow is usually have two distinct parts. One is the description of fluid motions without the knowledge of forces causing the motion. That means we do not want to know about the forces, but we know the forces have caused the motion, but to describe the motion is one very important part of kinematic studies. Another studies is the, based on this motion, what are the strain or the strain rates. As I told in the beginning, that the difference between the fluid and the solid is that under any infinite small tangential force, the fluid goes on changing its shape and dimension, which are known as strains, continuously. So, therefore, there is a continuous change of dimension or strain, and which are known as rate, which are expressed in terms of rate of strains. So, therefore, the rate of deformation or rate of strain, because of this strain the fluid body deforms, its dimension changes, its shape changes. These are also described by the fluid motion and the geometry of the flow, that we will see in this chapter. So, with this as background knowledge what the kinematics of fluid deals with, we will start the kinematics of fluid, the first part, the description of motion. Now, in a fluid continuum, fluid medium, flow medium, the motions are described by two approaches. One is given by Lagrangian, Joseph Lagrangian, and known as Lagrangian approach. Another is given by Euler, Leonhard Euler, known as Eulerian approach. So, there are two approaches or two methods of describing the fluid motions. Let us see what the approaches are. Now, first start with the Lagrangian approach. Lagrangian approach, okay? Lagrangian approach or Lagrangian method, whatever you call Lagrangian approach. Now, in Lagrangian approach what happens, as you know, the fluid medium, the flowing medium composed of several particles. The flow of fluid means the flow of several particles of fluid constituting the flow. So, in Lagrangian approach we study the motion or describe the motion of each and individual fluid particles. That means it brings about the kinematic information of each and every individual fluid particle. For a particular fluid particle, what is its trajectory or what is the displacement or the position with respect to a frame of coordinate system, what is its velocity, what is its acceleration. That means the kinematic information, mainly the position, the velocity and acceleration of all particles, of individual particles. So, here particles are important. So, a particle is identified. So, particle has to be identified. That means for each particle must have an identity. Then how do you distinguish one particle from other? The identity of the particle is fixed by its space coordinates at a particular time. This is the initial time where the investigation starts, when the investigation starts. Okay, that the initial time, for example, t is equal to t0, different particles have different positions. So, based on the positions the particles are identified. So, therefore, particles are identified by their initial position vector. For example, this is represented at S0 at t is equal to t0. That means, let us consider the identity of a particle is like this at t is equal to t0. That means, the initial time, the time when the investigation starts, his position is S0. Then the Lagrangian approach can be mathematically expressed as the position of the particle at any other time is a function of time, and this is expressed like this. That means, this tells that the position of a particle at any time t depends upon its initial location. That means, this is the identity of the particle and the time t. Clear? Now, if we have this can be represented in terms of a coordinate x, y, z, a Cartesian coordinate system. This can be written where we can write this position in terms of its x, y, z position like this, in terms of this, where I, j, k are the unit vectors along x, y and z. We can similarly decompose this position S0 with respect to the coordinate systems, that is position x coordinate, the initial y coordinate plus k z 0. I think you can understand. So, in this case we can write this as, if x, y, z is the coordinate of the particle which is given by S in vector notation, this is the position vector, then we can write the x coordinate is a function of x0, y0, z0 t. Well, similarly its y location is a function of x0, y0, z0 and t, and its z location is also a function of x0, y0, z0 and t. What does it mean? It means that the x, y, z coordinates of a particle whose identity is given by x0, y0, z0. That means, these are the decomposed in the direction of coordinate axis. The same equation like this is a function of the particle identity x0, y0, z0 and the time t. Well, so this is the description, and this way we write the equations for each and individual particle which varies in this location S0, that is x0, y0, z0 at time t is equal to 0. Accordingly, we can find out the way they disturb. Accordingly, we can find out this just wait. Accordingly, we can find out the velocity also. For example, we know that x is equal to x0, y0, z0 t. Similarly, we can now differentiate dx dt at x0, y0, z0. We can find out the velocity, the u component of velocity u, which will be, after differentiating this function, which will be again the function of x0, y0, z0 and t. Well, similarly we can find out the y velocity. This is u for x0, y0, z0 particle. That means a particle fixed. Similarly, if we find out the dy dt for the same particle x0, y0, z0 equals to the y component velocity. For the particle x0, y0, z0, you will find another function of x0. That means, this means we can find out the velocity components that also for dz dt. That means, for the y component of velocity also for x, the particle x0, y0, z0. This is extremely simple. Again writing this thing again and again, that means for the particle x0, y0, z0 will be expressed in terms of the coordinate x0, y0, z0 and the time t. That means in vector form we can write the same thing, that since we saw that we have seen that v is expressed now, we have seen that the s, that the displacement is expressed as a function of s0t, in vector form also we can write. So therefore if we differentiate this ds dt, we get v as a function of again s0, different function s0 and t. That means the velocity and similarly the acceleration, if we take the second derivative, I am not writing it again, you can see any book. That means if you differentiate this x function, that means this d square s dt square, then we get the acceleration. That means acceleration vector we can get by double differentiation of this, which will also be a function of, that means, and which can be written in terms of different coordinate system like that ax, ay, az as the acceleration, which means try to understand that the position of the particle, the velocity and the accelerations are find out for each and every individual particle, and this way the entire all the particles constituting the flow are being taken care of to describe its trajectory, its velocity, its acceleration, all the kinematic information. This is the Lagrangian approach. Now let me tell that there are one very inherent advantage and some inherent disadvantage of this method. The inherent advantage of this method is that when all the particles in the flow are identified and its histories are tracked or monitored, that means the conservation principle, for example the conservation of mass is inherent in it. We do not have to find out the, when we, for example when you do the particle dynamics, when a particular particle is identified and its dynamics is followed, nobody bothers about the conservation of mass, because the particle mass is conserved, we know the system mass is conserved. Similarly here when we track all the individual particles, they are identified and tracked, the conservation of mass principle is inherent in it. But the difficulty is that we have to cover a new number of particles in the flow that constituting the flow, and moreover if you now see these equations are little bit complicated in a sense. If we are provided with this equation that the velocity of a particle as a function of its identity, that is initial position and time, in terms of the x, y, z component this way, then if we have to integrate this to find out its trajectory, that means x, y, z as a function of time and the particle identity, sometimes the solutions of these equations become difficult. Now to avoid these difficulties, the another method has evolved, which is known as Eulerian approach, due to Leonhard Euler. Eulerian approach. In fact, Leonhard Euler was the academic advisor of Lagrange. Euler was much senior to Lagrange, and Eulerian approach is rather much simpler, which avoids this difficulty of Lagrangian approach, as I have told. What happens in Eulerian approach, you see, then you will understand this. Instead of tracking each and individual particle, giving an identity by its position at the initial condition t is equal to t0, what do? We forget about the particles, we fix a point. In a continuous flow of fluid, we fix points, different points. At any point, at any instant, we describe its velocity and acceleration at that particular point. That means here we concerned about a point in space coordinate. That means with respect to a space coordinate, it is the position which is very important, which is fixed. And what is done? The velocity is expressed as a function of the space coordinate and time. And similarly, the acceleration, that is dv dt, acceleration vector is also expressed as a function of space coordinate and time, which means that at particular space coordinate at a given instant of time, velocity is known and acceleration is known. It tags physically the information of particle like that at any instant. If I tell that this is the velocity at this point, that means this will be the velocity of a particle which arrives or which exists at that point. Similarly, this is the acceleration at any instant at a point, means the particle which will arrive at that point or exist at that point will have the same acceleration. Which particle is arriving, we are not bothered. So, this way we get the information of different points, information of velocity and acceleration at different instant of time, and this is expressed like this. This can be decomposed in terms of scalar components, that means the acceleration velocity in x, y, z component. That means if you see that this is x, y, z in a very familiar Cartesian coordinate system, then u, that means the x component of velocity, is function of x, y, z, t, where x, y, z are its coordinates at that point, that particular point, which is represented by this position vector x. This is x. Similarly, v, the y component of velocity, is function of x, y, z, t, and similarly the z component of velocity is a function of x, y, z and t. Well, and similarly the acceleration component a x can be written as function of x, y, z and t, and similarly a y can be written, this is a x, different functions. So, it is the different, that means here no particle identity, this is a space. A z is also a function of x, y, z and t. That means try to understand that here the velocity and accelerations are expressed as a function of space coordinates and time, another space coordinates at another time. So, that means it is a function of space coordinates and time, and the velocity at a particular location at a particular time is the velocity of the particle, and similarly the acceleration of the particle which exists at that point at that time. Now, we can relate Eulerian approach and Lagrangian approach this way. We can go from Eulerian approach to Lagrangian approach. For example, here you see that we have this expression given by Eulerian approach. This can be written in terms of the position vector ds dt is the function v s bar t, that is st. Now, if we integrate this with respect to dt, I think you understand. If you integrate this with respect to dt with the condition that initial condition, we are integrating with t. So, initial condition at t is equal to t0, s is s0, then simply you get an expression that s is a function of s0 and t. That means simply by integrating this information of velocity with respect to time with the boundary condition, initial condition, this initial condition tags the Eulerian approach to the Lagrangian approach, we get mathematically a solution. This is nothing but the description of the trajectory of a particle whose identity is given by S0, and that is the Lagrangian description of fluid motion. This way Eulerian and Lagrangian is tagged. Similarly, the Lagrangian approach which we saw earlier can be expressed in terms of the Eulerian approach if you integrate this equation, and at the same time what we can do, or sorry, we not integrate this equation, I am sorry, which can be done, the another one, yes, but differentiating these equations, if these expressions are there, differentiating these expressions and tactfully this becomes a mathematical job, eliminating this x0, y0, z0, because we know in Eulerian approach we have to express velocity as a function of coordinates, general coordinates, not a particular coordinates identifying a particle. That means we have to differentiate this, find out the velocity components in terms of x0, y0, z0, t, and tactfully we have to eliminate x0, y0, z0 and express the velocity in terms of space coordinates and time. So, you see in both the way the Lagrangian and Eulerian approach can be related. Now, this can be explained through a problem. Let us see a problem. So, this will be clear with you to you that how the Eulerian and Lagrangian approaches are related. Now, I read a problem in a one dimensional flow field. The velocity at a point may be given in Eulerian system by u is equal to x plus t. Now, a one dimensional flow field, there is a one component of velocity u which is a function of only one space coordinate. So, it is given by that x, and this velocity component u, that is not only a function of space coordinate, also a function of time t, as I told. So, this is an Eulerian description, u as a function of x t, and the function is u is equal to x plus t. Now, determine the displacement of a fluid particle whose initial position is x 0 at initial time t 0, that is his identity. So, what is the problem then? Let me do Eulerian approach, and let me do the problem. U is equal to x plus t. Now, what is u? I told you this, it has to be written in this form, dx dt. This is the Eulerian approach, that at any point x at a time t, this is the value. Now, if we integrate this with respect to t, integrate this, we will get the Lagrangian thing dt. Now, this integration is done in a tactful way, rather this is a differential equation. Directly it cannot be integrated like this. So, it can be integrated by writing in a different fashion. So, this if you write dx dt minus x, we write this way, d minus x. This is the way of writing. This is a linear first order differential equation where the operator d is d dt. Now, this equation, as you know already, this is very simple, that this has got two solutions, and complementary function and particular integral. So, complementary function will come from d minus 1, this gives a exponential solution a to the power t, where a is a constant, and particular integral will be found out by t, as you know, divided by d minus 1, which is nothing but minus t into 1 minus d, you have done it to the power minus 1, and if you expand it, you will see only minus t minus 1. So, therefore, the particular integral, I am not spending much time here. Now, if you put the initial condition in this equation, at because we have to find out the value of a, in terms of the initial condition, t is equal to t 0, x is equal to x 0, and if you put that, you finally get the expression as x is equal to, what is the final equation? X 0 plus t 0 plus 1. This is a simple substitution, x 0 plus, that means you put this, you get the value of a, t is equal to t 0, x is equal to x 0, then you put the value of a, you get the equation plus a e to the power t minus t 0 minus t minus 1. So, this is precisely the Lagrangian version. This is the displacement x for a particle identified by x 0 at time t 0. Clear? So, this is the Lagrangian version. Now, if I go to another example where this is from Eulerian to Lagrangian, another example that where the Lagrangian description is given and we have to convert it to an Eulerian description. A two-dimensional flow field where there are two components of velocities are there, but here in Lagrangian system it is expressed in terms of the x and y coordinate of a particle whose identity is x 0 y 0. You see the first equation is x is equal to x 0 e to the power minus kt plus y 0 1 minus e to the power minus 2 kt. That means it is a function of x 0 y 0 and t, and similarly the y displacement y is equal to y 0 e to the power kt. Now, we have to go for Eulerian. Now, Eulerian means what? Let me write that x is equal to, what is this? X 0, please tell me. X is equal to x 0 e to the power kt, x 0 e to the power minus kt, then plus y0 1 minus e to the power minus 2 kt. Well, and y is equal to y0 e to the power kt. Now, this is again I am writing which was described in the problem. Very simple, I told you earlier that here the procedure is that we have to differentiate, that means dx dt, that means in Eulerian approach we have to express the velocity in terms of x and t. First of all, let me see what happens. This if you directly minus kx0 e to the power minus, this is straight away differentiating. But here it is x0, it will not go because Eulerian expression u has to be expressed in terms of t and x y. So, x0 has to be eliminated. This is a simple mathematics. How to do it? You just make this x0, this is from here kx0 e to the power minus kt. So, x0 has to be eliminated. We have to eliminate d dt of, oh sorry, I have mistaken. So, here there will be another term, that is why I am mistaken, minus minus, that means it is plus y0 2k e to the power minus 2 kt, y0 2k minus minus plus. Now, if I, now what we do? We substitute x0 e to the power minus kt. So, okay, x minus, we have to express this x0 e to the power minus kt, that means this one minus k, this has to be eliminated tactfully. Now no fluid mechanics, x0 y0 has to be eliminated. Now, how to eliminate this? x0 e to the power minus kt we write as x minus y0, this one 1 minus e to the power minus 2 kt, follow, plus as usual y0 2k e to the power minus 2 kt. And if you do that, you will see minus kx plus ky0, here also ky0, ky0 minus minus plus 1, and here this is plus 1 minus and 1 plus, that means it will be 1 plus y0 into 1 plus e to the power minus 2 kt. It is okay? It is okay. Now, we substitute this y0 now, y by e to the power minus kt, that means minus kx. Then y0 is y by e to the power minus kt, then a minus ky, and e to the power minus kt, if I take it here, my plus e to the power minus 3 kt. And this is now dx dt, that is u. That means you see here no fluid mechanics, it is only a mathematics that you have to differentiate this to find out the x component of velocity, and you have to tactfully eliminate x0 y0 from by utilizing these two equations, so that finally u has to be expressed in terms of the xy coordinate and the time t. Now, y component is very simple, it is just a matter of few seconds, that y is equal to y0 e to the power kt. One can do it immediately, that v is dy dt, which is ky0 e to the power kt, and ky0 e to the power kt is y ky. Without doing it, one can simply tell that dy dt is ky is the differential equation for which this is the simple solution. So, v is equal to k, dy dt is ky. So, therefore, v is equal to ky and u is equal to minus kx. These are the expressions of velocity components as the function of x, y and t, and Eulerian approach. Okay. After this, now I will tell you certain important things about the flow, that what is meant by, now we see, now we will go with Eulerian approach. So, after knowing these things as information, we will accept that since Eulerian approach is much simpler in dealing with fluid kinematics problem and fluid dynamics problem, we will discuss everything in terms of the Eulerian approach. Now, the Eulerian approach, what is there? V is a function of, V is a function of space coordinate and time. So, in general, V is a function of space coordinate and time. It is expressed like this. Now, when the flow is not a function of time, then flow is not a function of time, that is known as steady flow. And when the flow is not a function of space coordinate, that flow is known as uniform flow. So, one has to understand the dependence on time indicates whether the flow is steady or not unsteady. For a steady flow, the flow velocity, flow acceleration will be independent of time. In fact, every parameter, all fluid mechanical parameter will be independent of time at any location. It may be function of space coordinates, but independent of time. That is the definition of steady flow. Whereas the flow will be uniform when it ceases, the velocity and acceleration ceases to be a function of space coordinates, but it may be a function of time. That means it may vary at a with time at a particular location, but it will not vary from location to location. So, therefore, we come like this, a steady flow, therefore, a steady flow is defined as, in general, V as a function of space coordinate only. This is steady flow, but non-uniform, because function of space coordinate is there, non-uniform. Similarly, a uniform flow is a flow which will not be function of space coordinate. The value will be same, and if it is so, the acceleration also will not be a function of time. I am not writing it again because it will be found by the differentiating the velocity. So, only I am writing the velocity. So, this will be a function of time only. That means it ceases to be a function of space coordinate, and this is known as uniform flow, but this is unsteady because it is a function of time. Now, there are two extremes. One extreme is that the flow will be both function of space coordinate and time. That means flow is neither uniform nor steady. That means flow is non-uniform and unsteady. Non-uniform, both functional dependence with space and time is there, unsteady. And another extreme is that V ceases to be function of both S and T. That means it is purely constant. That means the velocity is same at all spatial location, at the same time at any spatial location it is invariant with time. In that case it is purely uniform, another extreme, uniform and steady flow. Okay, uniform, and where the flow velocity and the acceleration also, the entire flow field given by velocity and acceleration is constant, is given by one unique value which is same at all spatial location and independent of time at all time intervals. Now, I give an example for that. Just give an example. Let us consider a flow through a pipe of uniform diameter. Let us consider the flow through a pipe uniform diameter, and let us consider the flow velocity both at inlet and outlet. Velocity both at inlet and outlet are kept fixed. That means the flow is coming at a steady rate with a steady velocity, that means which is not changing at inlet, and at a steady rate which is not changing at the outlet. So, what happens, you see? Now, we know, as Professor Suman Chakraborty has already told, because of the momentum diffusion through viscosity, that the property of the fluid, the velocity varies in the direction of r. But if you consider a highly turbulent flow, you will see the velocity hardly varies, it becomes uniform except at the surface where there is a variation of velocity and meets 0 to fulfill the no slip condition. Now, if you disregard this variation, in highly turbulent flow, the velocity is uniform in r direction, and in x direction the velocity does not change if the area remains same, the cross sectional area. This is the characteristics for a fully developed flow, which will be explained afterward. But at this moment we just consider in this way that we in a pipe where the cross sectional area is same in the direction of flow let x, and if we disregard the variation in r direction near the wall, the flow is purely uniform. For an example, I show you that if you consider the center line velocity, we will see that the velocity at the center line remains uniform. For a fully developed flow, it will not change in x direction, and it will be same for all other radial location. So, therefore, we can tell that with this x the velocity is same, that is the uniform flow, that is the example of an uniform flow. Now, if the inlet and outlet velocities are not changing, the velocities at any point will not change. That means the center line velocity will also not change. That means this line remain same for all t. That means we get a unique value of the velocity throughout, that means for all x and also for all r, and that also remains same at all t. So, this is a case of uniform steady flow where we get a unique value both with space and time. Now, if we have a condition like this, similar thing, that means this inlet velocity, the rate at which the fluid is coming same, that is inlet velocity does not change with time, the outlet velocity does not change with time. What difference I make? I make the tube little taper. Now, if we consider again the variation in the x direction, and we consider as if it is uniform across this transverse direction or the radial coordinate in this direction, neglecting the variation at the wall, we know this will be again dealt by Professor Suman Chakraborty afterwards. The velocity in x direction increases because of the reduction in the area to comply with the conservation of mass or volume flow rate. Okay? So, if you draw this, you will see the center line velocity, for example, if we draw, the velocity increases. That means the velocity changes with the x coordinate. This is a case of this is uniform and steady, uniform and steady, and this is a non-uniform, but now at the same time if the inlet velocity and outlet velocity do not change with time, these are the boundary conditions, then the velocity, for example, center line velocity which changes with x increases, but at any location it does not change with time. That means we have got the same curve for all t, for all t. That means it is a steady but non-uniform flow. That means it is non-uniform, here I write non-uniform but steady, not non-uniform but steady. This is an example. Another example I give you, the same thing here with this, but what I do here, this inlet velocity, the same thing in the pipe with the same diameter, I have drawn less because the space is not there, same thing, but with the variation of the velocity at the, that means inlet velocity and outlet velocity. For example, the inlet velocity is varying and accordingly the outlet velocity is varying. Then what happens? The thing is like this, that even if you have a constant velocity, because of this thing I have told earlier that cross sectional area is constant, the center line velocity is constant, along x direction you have a constant velocity, and this is x. Okay? But this will change with time, this will change with time, t is equal to t1, t2, t3. Now, if the inlet velocity is increased with time, then t will increase in this direction and velocity will change. That means velocity is constant along x direction, it is uniformity, but at any location the velocity changes from time to time. This is because a change in velocity at inlet and outlet from time to time. So, this is an example of uniform but unsteady flow. This is an example of uniform and unsteady flow. I cannot write this because of the shortage of space. And in a most generalized case, the problem will be like this. That means a tapered pipe will be there. Okay, I can draw it in a separate page. In a tapered pipe, the most generalized case that there will be the most generalized case is like this. We have a tapered pipe and the inlet and outlet may be varying with time. Then what will happen? Because of the taperedness, the velocity will change, and that variation will also change with time at different time T1, because this is changing with time, the inlet velocity, outlet velocity. So, there will be a space wise variation because of the taperedness, and there will be a time wise variation because of the changing in the inlet velocity and the outlet velocity. So, therefore, this is an unsteady and non-uniform velocity. Okay. Now, we will, after this we will come to the concept of acceleration. Acceleration. How do you define the acceleration of a particle? Now, let us consider the acceleration like this. Let us consider 2 points in a coordinate system. Acceleration. Let us consider the 2 points. First, let us consider one point whose coordinate is x, y, z, and let us consider another point whose coordinates are x plus very small distance from this. This is A, this is B, x plus del x, y plus del y, and z plus del z. And let us consider the velocity field here is u v w, x component velocity u, y component, z component w, and the velocity at the point B, neighborhood of A, is u plus delta u, because there is a change in the velocity, v plus delta v and w plus delta w. And we conceive the acceleration this way: when a particle moves from A to B, any particle, it is an Eulerian description, space coordinate, accordingly the velocity. From A to its neighboring point B, where the coordinates changes by a small amount, it suffers a change in velocity in x component by del u, y component by del v, and z component by del w, because this is the specified velocity at this point. Then what we can do? We can write u v w here as a function of x, y, z, t. Well, v is just now Eulerian description as x, y, z, t, and w is a function of x, y, z, t. Okay. Now, we can write for this u plus del u for this point where the velocity has changed by an amount del u because of the change in the space coordinate. Well, if this is kept in mind and written in a mathematical sense by expanding this function in the neighborhood of x plus del x, y plus del y, z plus delta z, and if we consider a particle while going from A to B takes a time delta t, because this is a neighborhood point whose coordinate this velocity is this, and a particle will reach from A to B with time delta t, then we can expand this as u plus, u is this function, is del u del x into del x plus del u del y plus del u del z into del z plus del u del t. Well, similarly we can write V plus delta V is equal to V plus this function if we expand in the neighborhood of delta x, delta y, delta zx and x plus delta x, y plus delta y, z plus delta z, del v del y delta y plus del v del z delta z plus delta t, I am sorry, del v delta t into delta t Similarly, W plus delta W is W plus, now it is okay, del W del x into del x plus del W del y into del y plus del W del z into del z plus del W del t into delta t. Now you see that this is the expression. Now if we just cancel u, v, w from both the sides. Now let us take this equation, the first one, u, delta u. Then what we get? Again I am writing this, delta u, the first one gives delta u is del u del x, again I am writing this del x plus del u del y delta y plus del u del z delta z plus del u del t delta t. Okay. Now if you make like this, plus of course there is one mistake. Now here I have forgotten to write that by Taylor series expansion, when you expand the function, this will be added with plus higher order terms in in del x, del y, del z and delta t. Similarly, here also higher order terms in del x, del y, del z, delta t. Here also higher order terms in del x, del y, del z and delta t will be there. We are not writing this thing higher order terms. What will be this term? As you know, del square u del x square into del x whole square. Similarly, del square u del y square into del y whole square. That means square of these terms will come. So, the higher order terms means square and more than that. That means del x square, del y square, del z square, del x cube, del y cube, del z cube, del t square, del t cube, all higher order terms will come. So, therefore, here also we can write this plus the higher order terms, plus higher order terms, higher order terms in del x, del y, del z and delta t. Now, if we make now this del u del t, okay, then what will be that? Del u del x into del x del t plus del u del y into del y del t plus del u del z into del z del t plus del u del t plus the higher order terms. Higher order terms. Now, these higher order terms, I am coming afterwards what will happen. Now, these higher order terms, before that I am telling you. Now, if we take the limit of this as delta t tends to 0. Now, limit of this delta t tends to 0. Now, limit of this as delta t tends to 0, limit of del x del t at delta t tends to 0 is equal to u. That means I can write u. Limit of del y del t at delta t tends to 0 is v. I am not writing. Again, this will take time. So, limit of del z del t at delta t tends to 0 is w. That means limit of, again I am writing, delta y by del t as del t tends to 0 is equal to V, and similarly limit of del z del t I am writing del t tends to 0 is W. Now, when we write this u v w, here you see these higher order terms will be divided by delta t, and when we write delta x as u delta t, so these higher order terms will contain the terms of delta t and its higher order and the higher order of delta t, higher order of delta t, higher order of delta t. And when we take the limit of this as delta t tends to 0, this becomes 0. So, therefore, what we get, limit del u by del t delta t tends to 0, which can be defined as acceleration. That means, it is nothing but it is represented as the derivative du dt, the derivative of u with respect to t. This is u del u del x plus v del u del y plus w del u del z plus del u del t. You understand? Now, I write it again by taking this term first. Therefore, we get the acceleration, that is the acceleration that is d u dt as what we get, del u del t plus u del u del x plus v del u del y plus w del u del z, that we get. Now, before explaining the thing, I write in the similar way if you do with the velocity component v, that means expanding this function. That means, if we do the similar way, the similar analysis with this equation and this equation, and in the similar way we arrive that dv dt is del v del t plus u del v del x plus v del v del y plus w del v del z. And similarly, we can write for the z component of velocity del w del t, the temporal one, plus u del w del x plus v del w del y plus w del w del z. And these are nothing but the acceleration in x direction, acceleration in y direction, and acceleration in z direction. Now, you see the physical concept. Now, the acceleration, that is the derivative du dt, contains this term. So, this is known as, this is the change in u with respect to time at any location, and this is known as, here also v, change in y component of velocity with time, and change in, this is the partial derivative with respect to t, which represents the change in the velocity with time at a given location, and this is known as temporal acceleration. In general, for any variable, this is known as temporal derivative, and this part is associated with the variation with space coordinates clubbed with the flow velocities. You see, the variation with the space coordinates clubbed with the flow velocities, and this is known as convective acceleration, and in general in terms of derivative it is known as convective derivative. So, therefore, you see the total acceleration is composed of temporal acceleration and convective acceleration, and this is known as, the total acceleration is known as material acceleration, or substantial acceleration, That means material or substantial derivative or material and substantial acceleration when the variables are velocity is equal to temporal acceleration plus convective acceleration. This can be written in a vector form. You see now that this can be written in a vector form. First of all, let me tell you that this can be written as vector form. This is del, that means grad of u, del dot grad of u. This is an operator del dot grad, because this is what? This is u del del x, del dot grad v del del y plus w del del z, and this is operated on u, gives u del x plus v del u del y plus w. Similarly, this operator, when we will operate with v, will give this. That means this is del v dot grad, sorry, I am sorry, v dot grad, del v dot grad, that is v dot grad, that is the v dot grad is this is the gradient, grad is I del del x plus, you know, this is the elementary vector calculus, plus k del del z, that is, and velocity vector is I j, sorry, I u plus j v plus k w. So, therefore, this is a vector operator v dot grad, which is this, which will be operated on u, will give the u direction acceleration x component, operated on v will give dv dt y component and z component. And if we write this in a general expression, we can write this in vector form, which is very much needed today, that acceleration vector is dv dt, which is equal to its temporal part, that is temporal acceleration, plus this is the convective acceleration. This v dot, this is operated, this vector operator operated on the velocity vector. This is temporal acceleration and this is convective acceleration. Now, I tell you this understanding is this is convective. Now, I tell you the understanding is that in a fluid flow, when a particle suffers the acceleration by going from one point to other point, that depends upon two things, whether the flow velocity is changing with time at any point, and at the same time whether the flow velocity is changing with space coordinate. As we have already seen that when the flow takes place, flow velocity does not change with time, then the temporal velocity acceleration will be 0. But if the flow velocity changes with space coordinates, even if does not change with time, so particle will suffer a change in velocity as it travels from one space to other. So, it suffers an acceleration because of convective part. And if it is an uniform flow, as I gave example earlier, then there is no change in flow velocities with space coordinates, but at any location it changes with time, then what happens? The fluid particles, when moves from one point to other point, it will have a change in velocity because the velocity has changed with time, you understand. So, therefore, it suffers acceleration because of temporal acceleration component, and both combinedly, the case where the fluid is non-uniform and also unsteady, the acceleration is contributed by both these two things. I give you a very simple example like this. It is a very common simple example, that for example, we start from Kolkata to Jamshedpur and we see that there is a rain at Kolkata, and when we reach at Jamshedpur, we see there is no rain. So, our conclusion may be like this, that because of the change in the location, rain is not there. Rain is there at Calcutta, rain is not there at Jamshedpur, and it may so happen if you ask a person by telephone to Calcutta, he will be telling yes, rain is here continuously, and if you ask the person at Jamshedpur, they will be telling there was no rain at all here. That means you make a conclusion that there is a change of weather or change of rain because of the spatial location. But it may so happen that you come to Jamshedpur and know that there is no rain, rain has just stopped, it was raining earlier, and you relate that to Calcutta, you know that Calcutta also rain has stopped. That means you have a conclusion that this is a function of time, not the space. It was raining everywhere, but changes with time, now it has stopped. So, when I have come from Kolkata to Jamshedpur in one occasion, I have seen the rain has stopped because of the spatial change, and in another occasion I have seen because of the change in time. So, both combinedly fixes the change of a quantity in a flowing medium, which is brought about by its change at a particular location with time, which is the measure of the unsteadiness of the flow, and at the same time it brings a sense that the change of the quantity with the advection, that means with the flow, which brings the concept of convective acceleration, and both together gives the concept of material acceleration, substantial acceleration, or the actually acceleration. So, I now give you a brief table that showing these different cases. You see that a steady and uniform flow, as I told earlier, both temporal acceleration, zero convective acceleration, there is no acceleration. That means if the flow is totally uniform and there is no change with time, there is no acceleration. And unsteady and uniform flow exists, that means there the temporal acceleration is there, because the flow is unsteady. At any location things changes, that the velocity changes with time, and therefore convective acceleration is 0 because flow is uniform. So, therefore, it has acceleration because of temporal acceleration. And the most steady and non-uniform, another case is steady and non-uniform. I forgot to tell the second one. The steady and non-uniform flow is steady. That means there is no change with time at any location, but because of the non-uniformity there exists an acceleration, which happens when the flow takes place through a convergent duct. That there is an acceleration from inlet to outlet because of the change in the flow velocities with the space coordinate. But at any location the flow velocity remains constant, no temporal but convective, and the total acceleration is contributed by convective acceleration. Come to the last, that is the most generalized condition where both these things exist, temporal and convective acceleration, means flow is unsteady and at the same time flow is non-uniform. For example, the flow taking place through a tapered pipe, as I told you earlier, and at the same time the flow changes, that means the velocity changes by changing the rate of flow. Okay. So, after this we will start now few things, that definition. Now, what is streamline? Definition of certain thing, streamline. Now, streamline is defined as a imaginary line drawn in a fluid flow at any instant of time, so that the velocity at any point tangent gives the direction of the velocity. That means this is the definition of a streamline. That means it is an imaginary line such that any instant of time. So, first of all, streamline has to be specified at any instant of time. It is a series of lines at any instant of time, so that at any point the tangent represents the velocity vector. Tangent represents the velocity vector. Now, in an unsteady flow, that is at any instant of time, since the velocity vector changes, that means the map of the streamlines, that is the series of streamlines, will go on changing from time to time. Okay. Now, since this streamline represents the velocity vector at a point at a given instant of time, two streamlines cannot intersect each other. If two streamlines intersect each other, then at any instant of time, since the streamline mapping is specified at a particular instant of time, there are two tangents and a particle, that means at any instant of time at any space coordinate there may not be two velocities. So, this is the reason for which the two streamlines cannot intersect each other. Now, what is a path line? Now, path line, at the same time we define it, the streamline comes as a consequence of Eulerian descriptions, where we represent the velocity as a function of space and time. So, streamline is like that, it is imaginary line in space at any instant of time where the velocity vector is tangent to that line. Now, path line is simply the locus of particle. I can write locus of particle of given identity, locus of particles of given identity. This is a streamline, and when streamline will be specified, it will be specified for the particles. That means this is for one particle, particle 1 P1 for example. This is for another particle P2, for another particle P3. This can intersect, two lines can intersect, even one line, path line can intersect. Why I am telling you? Now, in path line time is inherent. That means here this is a representative lines at a given instant of time which shows the velocity vector at each point which is tangent to this curve at that instant of time. But here you see that if you follow a path line, you are following with time. Time is inherent with the path line because this is the trajectory of a particle or locus of a particle moves with time. It can intersect itself, that means at some time the particle velocity is in this direction. When it comes, because of a circulatory motion in the flow field, it has come to the same point and has a different velocity. Similarly, the two path lines can be intersected at this point. This point can show different velocities at different time. When a particle has come for this particle P1 here, and another particle may cross here at different time. So therefore, the path lines are the locus of the particles of different identity, and they can intersect each other. A particular path line can intersect depending upon the flow field. So therefore, locus of identified particles, that means each path line is specified by a particle P1, P2, P3 like this, and time is inherent as we describe the path line. This is the representation of Eulerian approach, streamline and path line. Now I come before the definition of a straight line, I come the equation of streamline. So equation of path line is the equation of Lagrange. Equation of path line is S bar is a function of S bar, means that vector is S0 and t. Okay. The equation of streamline, now since at any point it is tangent, if we take an elementary length along the line ds, we can write V cross ds is 0, because this is tangent to this. So therefore cross product is 0, V cross ds is 0. Now if you decompose in terms of this Cartesian coordinate, if we decompose in terms of Cartesian coordinate, what we get? Decompose in terms of Cartesian coordinate x, y, z, then you get, and vector if you decompose in Cartesian coordinate, what you get? You get, if you decompose in Cartesian coordinate, you get an equation like this, I, j, k. You can write this cross component like this, then you can write this u v w d dx d dy and d dz equals to 0, and this can be written in space as an equation dx du dy by v, dx by u dy by v dz. So therefore the basic concept is this from the definition of streamline. Then it is the mathematical operations. We finally get the equation of a line in space this way. In a two-dimensional xy coordinate, dy by dx, we get this part is v by u, which means that the tangent represents the velocity vector. V is the y component of velocity, x is the u component of velocity. This is precisely the equation of streamline. Now another important line is there apart from streamline and path line, whether you now see the streamline originate from the concept of Eulerian approach, and path line comes from the concept of Lagrangian approach. Another line comes which is straight line, which is in between, and actually this is the line which we observe in the experimental flow visualization. Let me define what the straight line is. The straight line defines, just I give you the definition, then I will draw this. The straight line, a straight line is defined as the locus of the foot of all the particles at any instant of time which has passed through a given or specified point. You understand? That means this is specified by a specified point at any instant of time. Let us understand that. Let us have a specified point here, O. Now a straight line at any instant of time t will be, time is there, no? A straight line at any instant of time t will be defined as the locus of the foot of all the particles which have crossed this point O. That means this point O as given x0, y0, z0, a initial position vector. Now we consider that our investigation starts at some time t, a particle crossed this, and after that the particle has travelled some distance like this. And at an instant t, the particle, for example, we are considering a particle P1 which has travelled here from at some time t is equal to T1 from example. It has passed this point, particle P1, and at time t, when we are interested to draw the straight line, the particle has reached A. Now during this time from T1 to T, when the particle has reached A, the several times intervals are there. For example, T2, T3, T4 and so on, and different particles have passed through that. What happened to those particles? For example, the particles which are passed through this at an instant T2, within T1 and T, it has come to a point, it has come like this. Why this is different from this? Because when it has come at T2, time T2, another particle P2 for example, the velocity has changed here because of the unsteadiness of the flow. We will always consider a general case. So therefore, he will not follow the same trajectory which was followed by the earlier preceding particle P1 at time T1. He will follow a different trajectory. At some other time T3 within T1 to T2, the particle which has come or passed through this fixed point O will follow a different trajectory because the things are changing at the point O, the velocity is changing. Let it follow a trajectory like this. And here it is the foot at B, this is at t is equal to t, and at t is equal to t he has come to this point. And so on the particles will go. Now if we stop here, we will see at time t, these three particles which has crossed this point, past the fixed point O at time T1, T2, T3 has come to a point A, B, C at t is equal to t. Okay. Then if we join the foot of this along with a particle here at any instant t, one particle will be here which is crossing this point. So that will be the foot of this particle at that point because it has started here. That means that is the foot. So therefore we will take care of this. This is the straight line. So therefore the definition of straight line is that STREAK, STREAK, straight line is that it is the locus at any instant of time t, it is the locus of the foot or the feet of the different particles of different identity which have crossed a fixed point. That means straight line is specified by an instant and by the locus of the feet of the particles which have passed through a fixed point. So the fixed point and a particular instant are the two things to be specified for a straight line. Now you see at steady state what happened? At steady state, when time, this flow velocity is invariant with time, then streamline, path line and straight lines are same. How? I just explained here itself. Now a point P1 which crosses here at T1 follows a trajectory like this, and at time t it comes here. Now a particle P2 which will come at some time T2 through this, he will follow the same trajectory because when he comes here he faces the same velocity vector. So it moves like this, and any point if he goes, he faces the same velocity vector faced by his preceding particle. So therefore he will also follow the same line. All particles which will cross through this point will face the same trajectory. That means the trajectory of all particles are same. That means their feet are joined by the line which is nothing but the trajectory of any of these particles. That means the path lines of particles passing through this is same, and that is also the straight line, and at the same time this will represent the velocity vector at that point which does not change with time. The velocity of the tangent at this point remains same, invariant with time, because it is a steady flow. The velocity vector at a point remains invariant. That means the straight line merges with the path line and streamline. So therefore streamline, you yourself think streamline, this I tell path line, then you will understand much better. With this definition of all these three lines, the streamline, path line and straight line, you will see that the three lines differ very much when the flow is unsteady, but when the flow is steady, streamline and path line are same. This is because in a steady state the velocity fields at each and every point remain same invariant with time. So, therefore, if you follow the trajectory of a particle, the particle when we will reach a particular point, we will assume the velocity of that point which was arrived at by a preceding particle. So, therefore, the locus of the particle can be expressed in the similar way as the Eulerian description when we derive the velocity from the locus. Okay, that you have to see and you yourself have to think. So, this is about the first part of the kinematics. So, 2-3 questions, yes. We will take some questions and then, or we will start the, should we start the translation? Huh? Huh? 2-3 questions, okay. RCID 1263, yes, please. Yeah, please.
Sir, my first question is
Yes.
that in case of defining uniform or steady flow, you have mentioned only the flow parameter velocity. But if some other fluid properties or some other flow parameters are varying with position coordinate or time, but the velocity remains same everywhere and also with respect to time, in that case, can you say the flow will be uniform or steady?
Okay, very good question. Now, let me tell you, first of all, a steady flow is a flow where all parameters should be independent of time. This is the definition of a steady flow. So, if velocity is automatically for a steady flow, velocity is a function of time. Now, if a situation is such where velocity is not a function of time, but other parameters are function of time, this is not a steady flow. But in kinematic, we will consider velocity not to be a function of time. You understand me? So, therefore, a steady flow definition is that all parameters have to be independent of time, and an outcome of that is automatically velocity is independent of time. A uniform flow is a flow where velocity and acceleration have to be constant independent with the space coordinates. By other properties independent with the space coordinates are not defined as uniform flow. They may be defined flow with uniform density, flow with uniform temperature, flow with uniform property, the property which is invariant with the space coordinate. Uniform flow means it is the uniformity of the velocity and acceleration with space coordinates, independency. But a steady flow does not mean that it is only velocity. I tell you, a steady flow means everything should be invariant with time. A steady state system, a steady state control volume, afterwards I will tell you that a steady state means all parameters will be invariant with time, and velocity invariant with time is an outcome of this. And if velocity is invariant with time in any situation, other parameters do not do, then it is not a steady state, it is simply the velocity is invariant with time. Clear? Clear?
Okay. One more question, sir.
Please.
Yeah. One more question, sir.
Yes.
That is, suppose we want to visualize a streamline. We can do it with the help of a die that you have just told that we can generate streamlines and we can see. But in that case, we have to make the flow steady.
Yes, very correct, very 100% correct. Yes, yes, I am telling you, yes. That means flow visualization usually done for all steady state flow. In steady state flow, the flow visualization by die injection we make, and in fact what happens, I am telling you, when you put a die at a particular point and find out the thread streak which you visualize, that is nothing but the feet of those points which passes through that particular point where you injecting the die. So, therefore, you capture the straight lines incidentally in steady flow, that gives you the streamline. But an unsteady flow, this die injection flow visualization is usually not done. In practice, for such unsteady transient flows, we take the flow visualization by other method with the help of LDV or PIV. The entire physics is different by capturing the quantities at different time with a very short exposure, and then by correlating these two we find out accelerations and velocities by their from their displacement. This is entirely a different thing, but it is true that if you make the die injection experiment, That is steady flow you can make these streamlines. In unsteady flow, streamlines cannot be made by that experiment. This is by concept true, but it is not done in an unsteady flow. Okay.
Thank you. Thank you.
1241. 1241. RT. RCID 1241, please. RCID 1241. We can start translation, I think, or what is the time? 1328.
Yes, sir.
1328, please.
I'm Akash speaking from IIT Badal Engineering College.
IIT? IT?
IIT Badal, sir.
Acha, okay.
I want to know where we can apply the Lagrangian approach and Euler approach practically.
Now you tell you Lagrangian approach and Eulerian, okay. You have asked the question, okay, anything else? Okay, now
Yes,
Euler,
on the basis of design criteria.
okay, I
On the
tell
basis
you.
of design criteria.
Okay, I tell you.
Practically, where we can apply the Lagrangian approach and we cannot apply the Euler approach under those conditions.
Okay.
Similarly, for the Euler approach.
Okay. What happened is that you see that Eulerian and Lagrangian approach I have told. Now, usually in a continuum flow, continuous medium, we always make the Eulerian approach for our analysis because Lagrangian approach makes things more complicated, and I have told you this cannot be told without an example that a solution of the equations of Lagrangian type will be very difficult. But what is done in analysis, in case of certain dispersed phase, for example, I tell you the flow of solid particles in a liquid or gas, solid laden gas or solid laden liquid. In case of spray of liquid, liquid drops in a continuous gas phase. This type of problem, what is done, but the continuous phase, the liquid phase or the gas phase which carries these solid particles or the liquid particles in a gas, spray in a gas, liquid spray, then this continuous phase or the carrier phase is solved by Eulerian approach, the dynamics or kinematics. Whereas the discrete dispersed phase, which is dispersed, this is known as dispersed phase. For example, the solid materials which are carried by the gas, the liquid drops which are carried by the gas, the solid materials even carried by the liquid. So, these materials which are discrete particles and known as dispersed phase, their dynamics are usually solved by Lagrangian approach, and a tagging between the Eulerian and Lagrangian approaches are made through source terms. These are little difficult, this is done in the research, but in a continuous fluid flow without such discrete dispersed phase diffusing in the fluid flow, it is a typical two phase flow, two component even. When solid and liquid there are two phase, two component. So, in those cases only one Eulerian approach, another Lagrangian approach, but without this dispersed phase in a continuous fluid phase we always go with the Eulerian approach. This is the simplest approach. Everywhere we describe the fluid dynamics, dynamical parameter, the equations of fluid dynamics by Eulerian approach. Okay?
Right, sir. Thank you for the answer.
চলো ছেড়ে দাও একটু জল থাকলে ভালো হতো এরা 1218 RCT 1218 1218 please.
Hello, sir. Hello. Am I audible to you?
Yes, very much.
Sir, am I audible to you?
Yes.
Sir, what is the difference between the unsteady flow and the turbulent flow?
Oh,
The
yes.
question goes like this: are these both the things same thing, or they have any actual difference between them?
Okay, let me tell you. This will be explained more clearly.
Hello.
Yes, yes. Can you hear me? Can you hear me? Am I audible? Am I audible? Hello? No, no. Am I audible? No, you can. Yeah. Just again, you just.
No, sir, you are not actually audible to me.
Then
the voice
there
is
is.
actually hampering from the.
What happened?
So you are not actually clearly audible to me.
Okay, okay, okay. Just a minute. Just a minute. Am I audible? Am I audible? No, no. Huh?
You are not clearly audible. No, sir, you are not clearly audible to me.
But this will be documented afterwards. Okay, I tell you, you can listen to it afterwards. In fact, all flows,
Hello.
there are, in fact, hello, can you hear? In fact, all flows are inherently unsteady. Some fluctuations are there. Now, in a turbulent flow, I tell you, turbulent flow are inherently unsteady flow because there is always the fluctuations. But in turbulent flows, all the parameters which are fluctuating with time can be defined based on a mean value over which the fluctuation takes place. And with a time interval, this fluctuation ultimately dies out to gives rise to a value of 0 so that the mean velocity persists. That means in a turbulent flow will be steady when the mean velocity is invariant with time. But there is always a fluctuation over the mean velocities. So, strictly speaking, turbulent flow is unsteady flow. At any instant of time, velocity is fluctuating, but this fluctuation is over a mean value. It goes up, goes down over the mean value, and the statistical average of this velocity gives with time gives a mean value. If that mean velocity is invariant with time, we call the turbulent flow a steady turbulent flow. If the mean value is not fluctuating with time, this flow is known as unsteady flow. So, turbulent flow is inherently unsteady. Okay? All right, they will listen to it. Any other question? No.
We'll take the question later.